The idea now is to talk about self-conjugate matrix. When we're talking about self-conjugate matrix, is a matrix that its conjugate equals to itself by the definition. So what we will see is that if we look on the definition of a conjugate, which it should tell me just now, we'll see that it equals its conjugate, and it did show me. What about in inner product? So let's ask him. And I want him to show you the definition by the inner product. And this is it. You can see here that the conjugate, which is right over here, of the matrix A, which is self-conjugate, equals the matrix itself. And from here, you get the definition that the self-conjugate of a matrix in the complex space is the conjugate transpose. And when you look at this matrix, it's just the conjugate and the transpose of the matrix. In the real space, you will see that the matrix, which is self-conjugate, equals its transpose, so it's a symmetric matrix. In the complex space, we call self-conjugate matrix an Hermitian matrix, and in the real space, we call it a symmetric matrix. Now, when we're talking about the properties of Hermitian or symmetric matrix, which is self-conjugate matrix, I want you to show it to you. In the real space, when we're talking about self-conjugate matrix, we are talking about a symmetric matrix, right? Because I want him to show you. And he will. And you will tell me here, yes. In the real vector space, the self-conjugate matrix is simply a symmetric matrix, as you can see right over here. And when we are talking about the properties of this matrix, we are talking about real diagonal elements, symmetric, of course. Eigenvalues are real, which is a very important and useful property. All eigenvalues of Hermitian matrix are real, even though Hermitian matrix is in the complex space, all its eigenvalues are real. The eigenvectors of a self-conjugate matrix are orthogonal to each other. I mean, if you look on eigenvalues for different eigenvectors for different eigenvalues, they are orthogonal to each other. Also, diagonalization, you know that if you are talking about a self-conjugate matrix, you can diagonalize the matrix. Not just diagonalize the matrix, but you know that the diagonalizable or diagonalizing matrix is a unitary matrix, like you see here. And remember, unitary is a matrix where its columns are orthonormal to each other. Namely, each column norm of a unitary matrix is 1, and they are orthogonal to each other. So when we're talking about a self-conjugate matrix, we are talking about a matrix which we can diagonalize, and the diagonalizing matrix is a unitary matrix. So you know it can be, and you know what type of matrix diagonalizes. You also know that here in the diagonalized matrix, the eigenvectors on the diagonal are real eigenvalues, because we said that self-conjugate matrix has eigenvalues which are real. For example, if you look at this matrix and you take the self-conjugate or the conjugate transpose, you will get this matrix. So you know that it's a self-conjugate matrix in the complex space. There are applications in quantum mechanics, in linear algebra, of course, I'm talking about linear algebra, and numerical computation. Remember that, never mind. And you can look at it in the real space. And in the real space, we are talking about a symmetric matrix. Okay, so self-conjugate matrix means this one without the self-conjugate here. And in the complex space, we're talking about a Hermitian matrix, which is the conjugate transpose. And in the symmetric area space, we're talking about a transpose. We're talking about a symmetric matrix. And we have the very important properties. It's diagonalizable, its eigenvalues are real, and the diagonalizing matrix is a unitary matrix. Very important properties for self-conjugate matrix. Thank you very much. This was about the self-conjugate matrix in the real space and in the complex space. Thank you very much. If there are any mistakes or corrections, please write it down and tell me. And that's it for now. And thanks for JGPT for writing me the thing that I don't need to write because he writes for me.